Good morning, PTA superstars. This is Ichi Papa Nicola here, and I am going to present you a lesson on biomechanics. I am going to solve a problem with an arm and a man pulling a load using his arm. So you can see pretty much how those forces are developed in the world of biomechanics, and give you also a little bit of feedback on how to calculate torques and forces and directions within the scenario. It might look a little advanced for you as far as starting your PTA career now with us and being in this Kinesiology 1 class, but it's very important to understand how biomechanics work in our body and how the forces and torques and the energy gets distributed within our body. So the first thing that I'm going to do is I'm going to draw here the arm just the way it's stated in the example. So I'm going to draw it right here for you so you can see it. So this is kind of like a little picture of this. So I'm going to put the hand up here. And it is grabbing on, as I said, to this load here. So we have like this area right here where it's grabbing on and you're pulling. So there's a force going on the right side. This force is 8 pounds. So let's call it maybe F1. So this is the force. And then we have obviously our humerus bone right here inside that is going to give out some force obviously as well here. Then we have our muscle in this area right here. Maybe I'll use a little red to represent the muscle here. And then another bone down here to connect. So there's like the humerus bone in here. So we want to find out the force that's being exerted on the humerus bone. And that force is going in this direction as they're showing in the problem here to the left. So I'll call it F2. We do not know how large is this force. And then the rest, it's pretty much given here. So the rest of the areas here we don't have to worry about. Obviously, we have the bone in the middle. We can see the hand there. So a couple of things that we need to talk about here is distances, right? So when you're doing these biomechanic questions, you always want to know how far the force is located from your set point. And in this case, I think I'm going to use my elbow down here as my pretty much like pivot or my, fulcrum if you're doing like, the different like, sets here, or you can assume that this is the point that it's not moving. So this is going to be like a set point, and we need distances. So we're going to have to get some distances here. So we are given that this force up here is 13 inches from where the force on the humerus is, and then the force of the humerus and the humerus bone, the tension, however you want to call it, in the biceps muscle, as we can see it here, the bicep muscle is the red area, is another 1.3 inches, or actually is 1.75 inches away from the bottom here of the elbow, where we say like it's a set point, right? So this is kind of like you can think of this as like your pivot, your fulcrum, right? So nothing in that point here is actually exerting any torque. And to keep in mind, every time there's a corner in biomechanics, there are always a couple of forces. One is on the y-axis, one is on the x-axis, one is horizontal, one is vertical, and then this point right here is your pretty much like your point of pivot that you don't move. Now, if that corner is like this, like in this elbow here, then you're going to have a force going up and a force going horizontally, and then this would be the point where nothing is actually rotating there, right? So it's pretty much like your reference, right? Your reference point could be right here where all the distances are from that point. So, and of course, we do have a couple of forces acting there because it's a corner. So those couple of forces, we're going to have one of them is going to be going upwards, F on the Y direction, and the other one is going to be going on the X direction. And those are forces that we're going to be looking for to find in here. So, okay, so now what we're looking for is this F2, as we said. So we know, since this man is pulling a load here of 8 pounds with one arm, and it's held as shown here, there's no movement, right? So there's no kinetic energy or potential movement and such, right? We have torques coming in from those two major forces. So if we're just looking at the x-axis here, which is another word for the horizontal axis, we can say that the sum of all the torques is going to be equal to 0. Now, sometimes, like when I write this on the board, students get really intimidated by what is the sigma, Mr. Ricci, what is this tau, but again, the little tau, the Greek tau, is just another word for torques. And then when you see, if you ever see a sigma, that means the sum of all of them, right? So we do have also a definition that the torque is equal to force times distance. So not just the force itself, but how far are you from the reference point? So in this case, we have our F1, which is 8 pounds. And what we want to do is we want to multiply it by the distance from this force into the reference point, which is not just 13 inches, but also that extra 1.75. So it's 14.75 inches total. So that torque is trying to rotate the arm, obviously, in one direction, which you can say maybe counterclockwise. And the muscle, on the other hand, is acting the other way around, where it's trying to actually move this on the other, direction, which would be, clockwise. So that force would be, pretty much the F2 force. And then we want to multiply that F2 force as we, labeled it, times the distance all the way down to the reference point, which we know is 1.75. And we know the sum is 0, but we have to be careful. Sometimes the letter sigma, we think of it as like adding everything up. But in order for you to add everything up, all these forces, they must be going in the same direction. If they are going in opposite directions, that means that you are building opposite direction torque. And we can see here, that's why those arrows are so important, that one force F2 is moving to the left while F1 is moving to the right. So instead of adding them, we are going to subtract. So remember that you add forces together when they're all going in the same direction, whether that's right, left, top, or bottom, and you subtract forces if they're going on opposite directions. So what we're going to do now is I'm going to plug on the calculator 8 times 14.75. So that gives me 118 minus 1.75 F2 equals to 0. So 118 is equal to 1.75 F2. then I'm going to divide by 1.75, both sides, 118 divided by 1.75. It's going to give me 67.42857,143. So it goes on forever. If you want this to the nearest maybe 100th, then we know that F2 is equal to 67.43 pounds. So we found the answer regarding F2, 67.43 pounds here. The muscle obviously take a big, loss here as far as the force goes, but there is an explanation here. As Newton said, the bigger the force, the smaller the distance. The smaller the force, the bigger the distance. This is how you compensate. This is how the body compensates, right? So it's not just force when it comes to torque, but it's distance as well. So if you increase the force, you can decrease the distance. If you decrease the force, you can increase the distance. Those two go in opposite directions. Now, we might be wondering, what about the force in the humerus here in the bone? How much force is being acting on the bone? We got the muscle. We know the 8-pound load that you're pulling. But what about the force in itself here? So for that reason, we have to do a little more work in this component. So I'm going to be erasing my torques, and I'm going to be talking a little bit about these horizontal forces still on the x-axis. I'm not going to be going vertically in this particular question because there's no need. All the movement is happening horizontally. And we have 3 forces. We can see that there's 3 forces in the x direction. We have the F2, which we know now it's 67.43 pounds. We calculated it. We have F1, which is 8 pounds. And then we have this F of x, the force that it's coming out of the bone that's trying to protect, obviously, from any damage, right? And as Newton said in his first law of equilibrium, right, the sum of all the forces are equal to 0 if there is no acceleration involved here, and obviously there isn't any. Otherwise, they would have told us. So what we need to do next is we have to figure out, for example, are these forces going in the same direction? Are they going in opposite directions? So in this case, again, we add forces if they're in the same direction. We subtract if they're in opposite directions. So one thing that we can do in here is we can see that if I take F2, which is going to the left, I can add it to F of x, which is also going to the left. And then I can minus F1, which is going to the right. So again, F2 is going to the left, F of x is going to the left, F1 is going to the right. So you have to decide which ones you're going to add and subtract based on which direction those forces are going into. So be very careful like that. Even though the summation notation represents addition, forces are vectors. And as the chapter states, a vector, it's something that has 2 characteristics. It has a characteristic of magnitude, like size, and also a characteristic of direction, which is very important to keep in mind. So now that you've done this the right way, we've gone from sigma f equals to 0. Now we have our F2, which is our 67.43. We're going to add it to F of x. And then we're going to subtract the F1, which is 8, equals to 0. So 67.43 minus 8. So we get 59.43 plus F of x equals to 0. And so F of x is equal to negative 59.43 pounds. The negative, don't let that scare you. It's because of the direction. If they asked us about the magnitude of the force, like how big is the force, then it would be 59.43 pounds. But negative means that if you have decided all positive forces to be going on the right side, which usually it's what Newton does, uses positive direction, anything that moves to the right and up, and negative direction, everything that moves to the left and down, then you would be obviously like representing, with the negative, the direction of the force in here. So that is this question. One additional component that I wanted to talk to you guys all is if in any case the force is developed in an angle, not to panic. I know sometimes we're reading into the chapter here in kinesiology about the trigonometry section where we need to use some of the the angles and such, but there is a easier way to manage that. And the easier way to manage that is to imagine a right triangle like this, and imagine that you have a force going on a side like this. So it's on an angle, and the angle here, maybe it's like theta. So that angle can be any amount of degrees. Usually you cannot use this one on a slant because your x-axis are going to be going left and right, and your y-axis are going to be going up and down. So you always want to be orthogonal here. You always want to be on the x-axis and the y-axis. You do not want to be on obviously on a slant. So if you wanted to find the f on the y direction, all you have to do is take the f and multiply by the sine of the angle that is given. And the calculator has that button there, sine. And then if you wanted the x, all you want to do is take the f and multiply by the cosine of the angle. So in other words, if I have a right triangle and I have an angle here, any angle, like let's say 30 degrees, when you go across from it, that's sine of 30. And when you go in the bottom of it, that would be cosine of 30. So that is the easiest way to calculate that. So what I mean by that is if I do have a force, let's say like it's like 300 pounds, and this force is on a 30-degree angle, and I'm looking to find out this force here, the one that's going vertically and the force that's going horizontally, I can actually do that little triangle on the side here and say, okay, well, this is 30, this is going to be sine of 30, and the bottom it's going to be cosine of 30. And that's all you have to do. So you take the 300 pounds and you multiply it by sine of 30. So 300 times sine of 30. I'm going to put it on the calculator here. I'm getting 150 pounds going vertically. And then in the bottom, I have 300 times the cosine of 30. 300 times the cosine of 30. That's going to give me 259.81 pounds. So I was able to take a force that is a 300-pound force, but it's on a slant, which happens a lot of times in biomechanics. Not everything is orthogonal. I can split that force into two forces, one on the vertical, which is 150 pounds, and one on the horizontal, which is 259.81 pounds. So hopefully that helped a little bit with the representation of what those forces do, what the torque does. And if you have any questions, you know where to find me. Please reach out and let me know, what do you think about understanding the idea of what is a force, what is motion, what is energy, what's torque, and then everything else comes in time and with practice. So thank you for listening to this guest speaking lecture, and I hope you enjoyed it. Have a good day. Bye.